Okay, so the topic of this lecture is molecular dynamics. So we'll start with what is the molecular dynamics. So it's an advanced computational method, and the difference from all the methods we saw before is that it adds the time aspect to the simulations you are doing. Usually these simulations are done in nanoseconds up to several milliseconds. That's very long simulation. So usually in most cases we are in the range of hundreds of nanoseconds. That's usually sufficient for a majority of information we need to get. Computationally, it's very expensive. Usually we need the high performance or high throughput clusters. That is the HPC and the HTC you see. And nowadays, practically all simulations run using GPU acceleration, which is a specific kind of graphics card on the computer that is used to run very lengthy and very computationally expensive simulations. The whole point of this kind of simulation is to realistically, or the more realistically, or as realistically as you can, to capture the system of your interest, so usually a protein and some drug. What does it mean? It means that you include the solvent, you include the ions, you modify the pH, you are running the temperature while simulating, you're running the simulation while you also still computationally, but regulate the temperature, you regulate pressure. You can include some external forces, like for example, you have a ligand and the ligand is pulled or pushed inside some ligand, some ion channel or something like that. Molecular dynamics is widely used nowadays in effectively all domains of science. For us, of course, in pharmaceutical chemistry, it is the drug design. So you can computationally simulate the binding and unbinding of a ligand from and to a protein. You can also simulate how two proteins interact with each other, like the receptor and the antigen, for example, or in biochemistry, molecular dynamics is widely used to simulate protein folding or some more advanced molecular motors, for example. In physics, molecular dynamics is widely used to simulate the melting, for example. And in material engineering, molecular dynamics is used to simulate the nanomaterials and how they behave and what happens when you get the material to some extreme conditions. So you can simulate what happens at low temperatures, what happens at high temperatures, and more. There are a lot of uses. It's really very versatile tool in science. So what it is really, it's actually pretty simple. It's just a numerical solution to classical Newton equation of motion. So the very well-known equation F equals m times a. So mass multiplied by the acceleration. For each particle, we calculate the forces that act on them at the specific time. Then you take the particle and you move it very tiny bit, and you again calculate what changed with this particle, what are the forces acting on it at the position you change it to. And then you recalculate everything, so the forces, And you do this for a long time. So as I said, in nanoseconds and milliseconds, while this delta t, the time step mentioned in the third point, is usually in femtoseconds. What is a femtosecond? It's 10 power to minus 15. So here you have a very nice chart. I think very nicely representing how the molecular dynamics is done computationally. So at the beginning, you have your file. So you have an input file that contains the positions of your atoms. If we talk about proteins, for example, then you assign each particle, so each atom, you assign randomly based on Maxwell-Boltzmann distribution usually, which depends on the temperature you set. You assign the velocities, which is how and where are they going to move. And then you propagate it. So you calculate where every system will be after the time step. And then you calculate what are the energies, what are the forces acting on them. And from that, you calculate what is happening. So it's pretty simple. We are starting actually here. This is the first initial step. And then it goes to energies. Energies are always calculated from the force field, sometimes from the quantum mechanics, but that is so computationally extensive that you wouldn't be able to calculate in nanoseconds. You would be able to calculate some very, very few picoseconds maybe. So you calculate the energies, then you go to forces, and the forces you can see are related to energies. And from them you calculate acceleration, and then you go again and again and again. What does it mean that it's a numerical solution? Numerical solution means that there is no exact equation you can use to calculate what will happen to the system at a specific time. You need to calculate it, and you need to calculate it one by one, so each step at a time. You can't go from step 0 to step 155 without going through the rest. So a time step, as I said, is very important in molecular dynamics. Usually the time step needs to be significantly shorter than the fastest motion. What is the fastest motion? That's a very good question, because the fastest motion really depends on the simulation you have. If you have all atomic simulations, meaning that you are simulating every atom in your input file, then the shortest motion is of course different, as if you have some so-called coarse-grained simulations, which is a simulation that doesn't take each atom as a particle, but it takes okay, there are some problems with okay, if you can't see the slides, try maybe turning off and logging in again. Okay, if anyone has problems with the slides, just let me know, but should be fine. Okay, can you see the pointer now? There was no pointer until the third or fourth. No pointer. What about now? Can you see it? Can you see it now? Okay, it's strange. Okay, if it doesn't work, because I can see it nicely, so maybe there's something else going on. Okay, okay, I can try that. Okay, so we're at number 5. Yes. Okay. Okay, so as I said, the time step needs to be reasonably short, and it really depends on the system you use. If it's all atomic, it needs to be way shorter than if it's coarse-grained, meaning that you don't simulate atom as a particle, but you simulate several atoms behaving as one particle. So for majority of cases, the fastest motion is the movement of hydrogen on carbon. So that's why the fastest motion is chosen as the CH motion, and in this case you need to use femtoseconds, so 1 to 2 femtoseconds. And in this table, you can see what are the usual timescales of some biological systems and biological motions. So you can see that, for example, the folding and unfolding of proteins, which is in here, happens in matter of 10⁻⁻⁷ up to several thousands of seconds. So as I said before, we can maybe go to milliseconds. So we should be able to simulate finally even these large-scale motions. But a few years before, we were hardly able to simulate side chains and loops. So this is usually, and this is mostly based and due to the GPU accelerators that during the past maybe 5 years became so widely used and so efficient that we went from tens of nanoseconds to hundreds and to several milliseconds or either more. So the time step is always set at the beginning. If you use too large time step, then the simulation crashes because all particles try to move at the same time, and the simulation will just it's called a numerical crash. It will just crash, and the engine that calculates it will just finish it, and you will get the erroneous results. So as I said at the beginning, we try to be as close to real conditions as possible. So in this case, we want to include the solvent. There are 2 ways how to deal with this. The first one, the fast but very inaccurate one, is so-called implicit solvent. Implicit solvents are very basic. It's effectively just adding some dielectric constant, so a constant that describes the solvent in its physical manner to the equations that are used during the simulation. There are several theories how the implicit solvent works, and there are models used. One of the known ones are Cosmo model, for example. But there are others like continuous solvent, CPM or PCM, polarized continuous model, etc. And then the better one, but usually slower one, is an explicit solvent, which means that you really have your molecule of water, for example, in your system. It might seem pretty simple, but actually simulating water is not as simple as it sounds, because water can form clusters which are like very dynamic and very macro, and it really shows it to be a macromolecular entity, and it behaves differently than the usual water. So even the explicit solvent cannot be represented by a very easy model. So there are several models, and each model is used for different purpose. The more general one, and probably the most used, is the so-called tip 3 model, which treats water as a 3-point object. So you have 2 hydrogens, and then you have one oxygen, and those are parameterized using some values that are chosen to correctly replicate some experimental values. So if you think about it, you have a system which is composed of protein or of water, but then it's not infinite. So you have some boundaries that the system is in. So either you use no boundaries at all, so you effectively have protein in vacuum. This is very rare to use for biological systems, because it's effectively not close to real biological system. You can use it for something very short usually, or you can use it, for example, to simulate the evaporation, because then you don't have any border and the atoms can just go away, but it's still a bit inaccurate. Then you can treat the boundaries as rigid molecules. So you just take a molecule, you set it to some as a wall constraint. So you just set that there needs to be at least 10 angstroms of space between your molecule and the boundary of the box, and at this boundary you fix the molecule, and the molecule is just there and it doesn't move. So it's better than having no boundaries at all, but it can include some errors because the molecule doesn't move, so it doesn't interact as it should with the other molecules. The most used, and probably the only one used in drug design, is the periodic boundary conditions. So in these types of boundaries, you effectively simulate just a very small part, and you treat the rest as a mirror image. So you can imagine that this part that I'm pointing to is in the middle of a box, and on each side of the box you have the exact same replica of the box. So every time one molecule moves out of the box, it will be included from the box below or from the box that is next to it. And in this way you can effectively simulate how water flows, and it never changes some quantities, but it also has some errors that needs to be taken care of, mostly the electrostatic potential and electrostatic interactions, because you can imagine that if you have a molecule here, it needs to have some electrostatic interactions with molecules that are here, but there are no molecules. This is just a model that the calculation takes into account, but there are effectively no molecules, and these are definitely not the same as the ones that are here. So you need to do it somehow. There are ways to do it that are very efficient and they're correct. So you can effectively correct these errors with other ways, but it needs to be taken care of. During the simulation, you always need to decide what quantities are you going to modulate or regulate. These are called ensembles. One of the most used is the so-called canonical ensemble and isothermal isobaric ensembles. So in these two, you have the fixed number of the particles, then you have the fixed volume and the fixed temperature, or fixed pressure and the temperature. So in isothermal isobaric ensemble, the volume of your system can change slightly because the pressure shrinks it or enlarges it based on how the pressure is set. And in the NVT, so in the canonical ensemble, you don't regulate the pressure. So these are mostly used at the first stages, but the main stage of the simulation is usually run at NVT ensembles. So how does it look? When we take MOI, for example, you always do the molecular dynamics in stages. In the first stage, you need to minimize the system. So it works very similarly to docking. You take the protein with your ligand or another protein, then you correct all the mistakes. And here it's very important to have the full protein. In molecular docking, it doesn't really matter if you choose to build the loops or just cap it. But in molecular dynamics, you need to be as close to the real conditions as possible. So if you have a loop somewhere in the molecule, you need to have the loop there. It doesn't necessarily need to be correct, because during the steps, these loops can be changed and they move a lot, so they should attain the conformation that they should have in most cases. But you just continue with the preparations as you would do for the docking, and at the end you solvate your system. So you take the protein and you put it into a box. You fill the box with the solvent, usually water, and then you minimize it, because every time you add something to the system, it's added based on some very simplistic rules for it to be fast. But then you want it to be a real system, so you need to minimize it to get rid of all mostly geometric clashes. So the atoms that are very close to each other need to be slightly shaken and put into right place. So the minimization is usually very short. It's in a matter of picoseconds, and then you need to heat your system up. And what does it mean? Heating actually means that it starts to move, and the hotter it is, the faster it moves, in a very simple way. And then when this is done, it needs to be done very rigorously, slowly, because if you go from 0 degrees to 100 degrees, or in this case, this is in kelvins, so 300 kelvins corresponds to 27 degrees, I think, Celsius or centigrade. So if you go from 0 to 30 degrees, then you need to go very slowly, because if you go fast, then the molecules will go from literally standing to moving around very fast, and it will crush it again. So the system will behave differently than it should. Then you equilibrate the system, meaning that you leave it using the ensembles that we defined before. Usually you start with NVE and NVT, so you have this fixed number of atoms and fixed volumes, and then you usually fix the temperature, and you leave the system for some time until it reaches some kind of equilibrium. Then you add the pressure, so usually it shrinks a bit, but again you leave it until it reaches some kind of equilibrium, that it's not moving too fast or moving too long from moving too far from the position that it was before. And when your system is equilibrated, meaning it's not changing anymore, you can start so-called production phase. And the production phase is actually the phase that you are mostly interested in. And this is the longest part. So in this case, this is 100,000 picoseconds, which is 100 nanoseconds. And this simulation is what we are interested in and we get the data from. So it's usually in trajectories, in files, either binaries or text files, but it's usually at least hundreds of megabytes of information. So apart from fast machines, you also need a lot of space and computational storage to save all the files in. After this is done and you run it for as long as you want it, you can cool the system down, but this is usually not done for the purposes we use it. But it can be used in other applications, like, for example, conformational stabilities and conformational searches, etc. So this is just a description of what I said. So you prepare the system, you correct all the errors, you solvate it. You need to select which solvent. It's usually water, but it can be also something else. You set the pH. What does it mean? It literally means that you just computationally define each acidobasic group if it's in protonated or deprotonated states. There are specific molecular dynamics protocols and simulation parameters that can change the pH, or you change the pH during the simulation, and that has the effect also on the protonation. But those are more advanced, and you need to know what you want to study. Then you put it in a box, as I said, but it actually doesn't have to be a box. It can be even something else. It can be octahedrons or some other very specific 3D structures that are supposed to minimize the number of waters that are unnecessary in the simulation, because not all waters are close to the protein, for example. So those waters are effectively just slowing down your simulation. If you take a box and you have a globular protein, it's in the range of maybe 30–40%, or 30 to 40% of waters are actually just there to be calculated, and they don't really add anything to the simulation. So if you don't have them there, it's very, very fast. Then you define what type of boundaries do you want to use. It's usually periodic boundaries. You need to add ions. This is done either to neutralize if you have a lot of non-neutral amino acids, or you can use it to set the osmotic pressure, usually to 0.15 moles per liter. And then you go through the minimization and all the steps of equilibration, and at the end you run the simulation. It's best to run the simulation at least 3 to 5 times for the statistical reasons, because every time you start the simulation you can get slightly different initial velocities. So the positions of each atoms are slightly changed each time you do the simulation, and this is actually closer to what in reality happens. So not every protein behaves the same way, every other time. And then when everything is done and you got your gigabytes of data, you need to analyze it somehow. So you can do it 2 ways. The easier but not really reproducible way is a visual inspection. So you can just take your trajectory files and just run it as a movie, or you can just set specific snapshots or screenshot, but in molecular dynamics it's mostly called a snapshot. So you can just check the picture, like I can see or I don't see something happening. Or you can do it the proper way, the scientific way. So you just take the data from the simulation and you plot it. And there are specific kinds of data that are used in molecular dynamics simulations. The most important ones are the RMSD, RMSF, but you can also check some other variables and some other computed properties like radius of gyration, etc. And all this information are supposed to give you some idea about the system, how it evolves in time, how it changes, or if it changes, if it doesn't change, if it changes much or not much. So we'll go through the basic ones. So RMSD, or root mean square deviation, is probably the most important measure of the system. It's supposed to tell us about how much one state of molecules differs from the other state. So in terms of molecular dynamics, we're usually talking about how the molecules changed from the initial state. So you just take the state at time and you compare it with another state at time 0, and you do this for all or every 10th to save time. And you plot this information in a plot, and you will see the plot very shortly. Usually you do it for all atoms except hydrogens, because hydrogens are usually moving a lot and it doesn't really mean anything, it's just hydrogen. But what is more important is the backbone atoms or alpha carbons, or something that is not supposed to move that much, because if it does, then it means that the protein itself is moving, if we talk about proteins. You get one value of RMSD for each time, and this value corresponds to the system, usually the whole system, as I said, but you can choose one subset and compare this, for example, the helixes to beta sheets, etc. And you will see that the helixes are usually rigid, while the loops are not rigid. And again, beta sheets, these are rigid subsets usually in proteins. It's mostly used to determine when something in molecule happens or doesn't happen, and not what happens. It's just when. The answer to what is usually up to the researcher to go through the simulation and to see what happened. This is how it looks. You take the initial state, you take the state after that, and you compare them. As you can see in this picture, there are some differences in position of these corresponding atoms. If you plot it as a graph or as a plot, it looks like this. So this is time 0, so you always take one each time and you compare it to 0, and you go and go and go, and each will give you a point, and it looks usually like this. So the lower one corresponds to alpha carbons, while this upper one corresponds to all atoms. Even though this upper one is higher than the lower one, it doesn't necessarily mean that it's wrong. It's just you have more atoms, so of course you have a bit more difference in the positions. The other important measure of difference or measure of flexibility is the RMSF. It's the root mean square fluctuation. This measure is used for individual atoms or individual residues. And it's supposed to give you an information about which atoms or which residues in the system are moving the most. So it doesn't tell you when, it tells you what. Looks like this. So in this plot, you see all the atoms. You have some 1,000 or 950 atoms. And here you see the measure of movement in nanometers. And as you can see, you have 1, 2, 3 atoms that move a lot in the simulation. Then you have some that move somewhat, but not that much. And then you have these atoms that are on the bottom, like here, for example. All these parts that are here and here are the atoms that move the least during the simulations. I will show you some real examples later on. You will see that it really makes sense. Visually, you can analyze it mostly using colorings. So, for example, here you see some alignments of different times of the same system. Red one is the initial state and the blue one is the final state. And as you can see, these parts which are the conserved and these parts which are corresponding to the alpha helixes are mostly at the same place. But for example, this part here, which is a big loop, moves a lot. It was at the beginning it was here, but at the end it's in different place, in completely different position. The same you can do for a subset of atoms. Here, for example, we were looking at histidines that are complexing one atom of a metal, and you can see that they're pretty much still at the same area, even though they're moving a bit from their equilibrium. So this is one way. You can take the snapshots and you can just align it and you will see where is the difference, or you can just calculate the RMSD or RMSF, and then you just take, for example, the initial state and you just plot the colors on top of the molecule, and you will see that in this case, blue thing is something that is moving a lot, while the red thing is something that doesn't move that much. So as you can see, the blue thing is again this loop, and this loop is the same as the loop on the left side. So you can see that in both these analyses we got to the same idea, that the loops are very flexible and they're moving a lot. But on the right picture, we can even see that it's this particular amino acid that moves that much, or the other one is here. For the data plots, these are real data that we got from one of our simulations. We usually take into account the RMSD value, so how big it is, and then we take into account if it changes, if it moves, if it diminishes. If it's at the same range, so it's around 2.5 and it doesn't change, then it's usually fine. If you had one value reaching around 2.5 and then something would happen and it would go back or it would go up, then it usually means that there is some very big conformational change. So usually it means that it wasn't equilibrated well enough from the previous stages. It's always good to run the simulations long enough, because if you are trying to see, for example, the conformational change like an opening or closing of a loop, and you know that it takes a few nanoseconds until it opens, then you should wait for it to close again, and then to open again, and then to close again, because from this you can get some kind of statistics about opening and about energies necessary and stuff like that that you will calculate later on. But if it only happens once and it doesn't go back, then you don't know if this is an error in your simulation, because that can happen as well, or if it was supposed to happen. Also, you can see here that the temperature was set to 300 degrees, so it increased during the heating stage. Then it went down a bit until we started the equilibration again, and then it went to 300, and then it oscillated around the value of 300 plus or minus maybe 5 or 10. But for the pressure, you can see that it goes really from minus 100 to 100. We set it to a value of 1, which is 1 atmosphere, and it still goes from minus 100,000 to 100,000. So the pressure really oscillates, and it depends on the algorithm that you use. It depends on the system, but if the value is close to what you want, at least the average value, then it's usually fine. For the RMSF, again, you have the residues here, and you can see that the residues between 142 to 51 and 52 maybe. So these are the most flexible, and their RMSF is around 7 angstroms. So it means that they change the position within 7 angstroms in a very simplistic way. Mostly the secondary structures like beta sheets and alpha helixes are in the parts of this plot that is lower, and the loops are usually the ones that go high. So the application of MD, as I said at the beginning, you have a lot of research areas where you can use it. For example, in MOE we have low MD protocol that is used for conformational analysis, and it's called a low MD protocol, and it is very simple actually. You just take a molecule, then you heat it up, and while heating it you increase the energy that the molecule has, so it can achieve some minima, some maxima. But you're never sure if you achieved the global minimum. So if you cycle the temperature from 0 to, let's say, 500, and then you do it again and again and again, then you should be able to statistically obtain all the necessary and all the important minimas and maximas of the molecule, and then you can really work with that later. There are also some other like equilibrium properties in proteins. This is just for illustration. These things you can download and you can try it yourself. These are freely available on an AMD and VMD website of University of Illinois, I think. Nowadays, it's not that important, but there's still a lot of proteins that we know the primary sequence, but we don't know the 3D structure anymore, or still mostly. There are some new ways like AlphaFold, if you heard about it. It's an algorithm based on machine learning and artificial intelligence that is supposed to give you the correct prediction of the 3D structure of a protein. But before we had this kind of innovation, there were other methods, like for example taking the linear sequence and running very long molecular dynamic simulation and hoping that it will achieve the right conformation. It wasn't very successful, I would say, because sometimes the protein can achieve the conformation as it should, on its own, but usually the proteins need some other proteins that help them to correctly assemble some parts and continue on its own later, so you wouldn't get it from the normal molecular dynamics simulation. There are so many softwares to work with in MD, but the most known ones, most of them are free to use, is the NAMD, which we have here at our labs. Then there's Ember, Dismon, Gromax. There's so many more of them, but usually they are based on one of these two. Then there are some other things to consider, like what type of force field do you use. There are some force fields that are named based on the software that it uses. For example, the Ember force field is the name of the software as well as name of the as the name of the force field, and it always improves along the way. They always are able to improve its accuracy by adding some special cases, but they're very accurate now, more accurate than they used to be. You can find a lot of information on this website. It's click2drug.org and some other, or you can go to these websites, and they usually have either the tutorials for their software, but most of them also have some tutorials and information about the molecular dynamics on its own. Okay, so here I have some interesting let's get a look at binding of donepezil. So this is how a molecular dynamics simulation looks like. This is the result actually. So on the right hand side you have the plots that are being shown in real time. It's not usually done like this because it takes a long time to calculate it. You can see that it took 10 nanoseconds to run this simulation, but there is one very important thing, that this was not ordinary molecular dynamics. It was accelerated in a specific way, so they knew how it's supposed to go. So they were just taking the donepezil molecule and they were pushing it inside. And you can see that now it seems like this is the equilibrium state, because it's not changing from the 3rd nanosecond. In here it started to plateauing, so you would say, okay, this is the end of the simulation. But if you wait for a few seconds more, you will see that it abruptly changes, and then it achieves the conformation that is known from the crystallographic structure actually. So still nothing happens. It's like 9 nanoseconds so far. And now it changed, and now it achieved the conformation that is known. Here they have some, this violet pinkish color is the molecule taken from the crystallographic database, and you can see that the RMSD value between the selected computationally and crystallographically got positions is around 1.4 angstrom, which is very close. For the protein folding, as I said, since this is one of the used method, this video is a comparison of several microsecond simulations of different force fields. So they took one protein or one very short peptide and they just left it in different conditions, but the conditions were differing only by the used force fields, and you can see that they behave very, very differently. So except the difference of the initial state and initial conditions and the used algorithm, there is another thing to consider, which is the force field that group used. If you want to work with molecular dynamics more, there are some subtle differences and there are some more important differences to take care. In this particular case, I think amber force fields were one of the best, and they were very close to obtain what was supposed to be. And so if we get to one of the final steps, you can see that, for example, in here, in charm force field, this is supposed to be an alpha helix, while in amber, this looks completely different. And in all amber force fields, it looks different. So you need to be really careful about how you interpret the results of molecular dynamic simulations. Okay, we can check this introduction to molecular dynamics. Okay, this is effectively what we saw in the first slides. So we always treat the molecules in a very simplistic way, like a usual Newtonian type physics, even though we all know that molecules are more quantum behaving particles. So this kind of treatment is used because it's very easy to calculate, even though there are some errors that arise from this. The most important one is that you can't really form or break a bond on its own when they should or should not be broken. If you treat the system in a quantum mechanic way, that is computationally so expensive that you can't really do it in usual manner as you would do for other mechanical interactions or mechanical simulations. But there are ways to do it. For it's mostly used for catalysis simulations. You can check some videos online that show, for example, how a hydrolysis of a bond looks like in reality or simulated, of course. And so these three things he mentioned, 3-point charges. This is the tip 3 model of water. There are other models like tip 4, tip 5. that add some other definition to water that is supposed to be used for more detailed description of the behavior that the water can represent when it interacts within some space. Yeah, so this is very important. As he said, all the results are dependent on how well your system is parameterized, meaning how well can you simplify the interactions that happen using usual physical properties and not including quantum mechanics. So some molecules are very easy to parameterize because they don't have very difficult to even imagine interactions or properties, and there are some molecules that are so hard to parameterize that you can't be really sure about the results, and you need to run it multiple times to see if it changes very much or not. Garbage in, garbage out is a very nice way of saying that if your data is bad, when it goes into the simulation, the data you get from the simulation is useless because it doesn't represent anything. Actually, it's just a waste of resources that you used for the simulation. So you need to be sure that, and with the molecular dynamics, it's even more important because it usually takes very long time to finish with the simulation. So you need to be really sure that the information you put in is a reasonable prediction, and it's not just something you would like to try. Okay, so I think this is enough. Then we have the last one. It's the ligand unbinding. So we saw how does it look when donepezil enters, and now we will see how does it look the other way. By the way, all this information you get, so For example, the information you can get from this particular kind of simulation, you can use to extrapolate and calculate what is the energy of binding. So you can compare different ligands between each other, and you can compare how well are they able to inhibit or at least bind to some specific target or protein. Okay, as I said, there is also a way to simulate some physical properties like ice melting. This is very basic and not really useful for pharmaceutical chemistry, but it's used in pharmaceutical technology. You can simulate excipients interacting within some kind of grid. You can simulate what will the excipients do in a tablet, and you can simulate different kinds of excipients, how and which one of them is best. So there are numerous ways you can use molecular dynamics in the research, not only for drugs. Let's get to the melting phase. So they started heating, and as you can see already on the top, the lattice of the on the water starts to break as the temperature increases, and this is actually what the melting looks like. So you have a crystalline water structure and it starts melting, and the water just goes away, and it should fly away in gaseous state or as water, liquid water. Okay, so this is all from me. If you have any question, I'm happy to answer.